In our last class, we saw finding transient response by mode superposition method. In this lecture, we'll see how to find the transient response using recurrence relation, which is actually coming from finite difference method. So you have seen that in these propagation problems we have made a partial discretization where the space was discretized using finite elements, but the time was not discretized. So after discretization of the space as finite element equations, we got ordinary differential equations in time, and those ordinary differential equations in time can be solved either by mode superposition method or by a finite difference in time, which is also known as a direct integration in time. And that means we derive a recurrence relation which actually relates the value of the variable phi at a time t plus delta t with respect to the value of phi at a time t, where delta t is the time step. So we have to write a recurrence relation based on finite difference method that relate phi at one instant of time t to values of phi at a later instant of time t plus delta t, where delta t is the time step. Now this recurrence relations, this direct integration or whatever you say, or finite difference schemes, they start from an initial condition at time t equal to 0, and then step by step they march out until they reach a first final desired time of your interest. So a popular family of time marching algorithms is considered for this purpose. So here is a finite difference, a family of finite difference methods which depend on a parameter theta. So based on a parameter theta, a family of algorithms can be developed where they write the time t theta as Tn plus theta delta t, where theta is from 0 to 1. Now this is your equation. So at t theta, the equation is kt phi dot theta plus k phi theta. We are assuming ktt is 0. Phi theta is r t theta. So this is the equation at time t equal to t theta. And we assume that phi dot theta is equal to phi at time n plus 1 minus phi at time n tn divided by delta t. But phi theta we interpolate between phi at n and phi at n plus 1 using this. So phi at t theta is equal to 1 minus theta into phi at tn plus theta into phi at tn plus 1, and the right hand side is 1 minus theta into the right hand side at time t equal to n, and theta into the right hand side at time t equal to n plus 1. Now if you substitute these values of phi dot theta, phi theta and r t theta in here, you get this equation. So theta plus 1 by delta t kt phi n plus 1 equal to this plus this. So this left hand side, the coefficient in the left hand side is denoted by k bar, which we call the coefficient matrix in the left hand side, and these terms together we call the force vector, effective force vector at the in the right hand side. And if theta equal to 0, the method is known as the forward difference scheme. If theta equal to half, the method is known as the Crank-Nicholson scheme. If theta equal to 2/3, then it's Galerkin scheme. and if theta equal to 1, it's a backward difference scheme. So ultimately you are left with a task of solving k bar phi n plus 1 is equal to r bar n plus 1. So now what are explicit and implicit schemes? So the time marching algorithm which we have just described, a time marching algorithm which requires the solution of a set of simultaneous algebraic equations at each time step is called an implicit algorithm. But in an explicit scheme or in an explicit algorithm, at each time step the nodal unknowns are determined from uncoupled algebraic equations. So for implicit schemes we have to solve coupled algebraic equations, but here the algebraic equations are uncoupled. But how these algebraic equations are uncoupled, that we'll explain later. But here you must you must be in a position to appreciate that explicit algorithms avoid the solution of simultaneous algebraic equations at each time step are and hence are more economical. But the for explicit integration schemes, to make them stable, the time step must be less than a critical value. So your time step which you can use for explicit schemes are much smaller than what you can use for an implicit scheme. So here, though you avoid solution of simultaneous equation at each time step, but you have to use much more time steps, and your advantage, computational advantage, is thus offset. So, here actually this is actually our recurrence relation. This is actually our recurrence relation which we shown here. So this is our recurrence relation. We are again repeating it here. Now for forward difference, suppose you are taking a forward difference scheme where theta equal to 0. So theta equal to 0 means this goes, this remains, this theta equal to 0, so minus k is there, plus delta t kt is there, phi n plus 1 minus this remains, rn, this goes. Okay, so in many cases it is possible to approximate this kt as a diagonal matrix. So if that is so, then this is a diagonal matrix. So the equations at phi n plus the unknowns in phi n plus 1 actually becomes uncoupled, and you can solve this without solving simultaneous algebraic equations. Now this is the solution sequence for an implicit algorithm. So you have to form KTE and KE for each element. Then you have to initialized phi n at time t equal to 0, that you have to take phi 0. You have to select a time step. Then you have to assemble the effective coefficient matrix k bar. The effective coefficient matrix, which is this one, the effective coefficient matrix k bar, from the element matrices, and then you have to modify this k bar for boundary conditions. Then you have to factorize this k bar. Suppose you are now familiar with the LU decomposition scheme or LDLT decomposition scheme. You can factorize it using a LU decomposition scheme. Then at each time step you have to find out element right hand side vector and element right hand side vector at time t equal to n plus 1. It is at time t equal to n. So from this you have to, you know what is Rn plus 1, Rn e at Re at n plus 1. Then you have to assemble to get the effective right hand side, that means the whole thing. So that also requires the knowledge of k and kt, and then you get r bar n plus 1, and then you modify r bar n plus 1 for boundary conditions, and then you have to solve for phi n plus 1. This is already factorized, so just from this factorized this you can solve this, and at each step at least you don't have to factorize. You have already factorized it initially, but still there are lot of computations involved in this, especially for problems of large size. And for explicit algorithm, again this is same, this is same, this is same, but here you have to assemble the diagonal coefficient matrix, and the effective right hand side is nothing but kt here, because here if you put theta equal to 0 for forward difference scheme, which is an explicit scheme, then this part is not required, only this required. So you need only to assemble kt, and you have to modify kt for boundary conditions, element vector at time n tn, assemble the right hand side rn plus 1, and here r bar in r bar n plus 1. So these are the terms present. So if this is r bar at n plus 1, then modify r bar n plus 1 for boundary conditions and solve, modify sorry, r bar n r bar at tn plus 1 for boundary conditions, then solve for phi n plus 1. Here this is the solution. Suppose this is a diagonal matrix like this kt here, and you want to solve these equations, then solution is just a division by the diagonal element. Divide the corresponding right hand side by the diagonal element. So here there is no there is just one division is required, and no more calculations are required for determining the unknowns. So you from here you can understand that explicit scheme requires much less computation, but the number of time steps required are much more. So here this was our equation, starting equation. Now we will study the stability of these schemes. So how is the stability found out, that we'll see in this derivation. So we start with this, and we calculate the eigenvectors of the initial equation, homogeneous equation. So this is the initial equation, and we find out the eigenvectors of it. So you just k phi bar equal to minus lambda kt phi bar, and from here we see that this is equal to this, or for L equal to A, phi L transpose k phi bar. So this is the eigenvector, so equal to minus lambda k, and we assume that the eigenvectors are kt orthonormalized. That means phi L transpose kt phi k is equal to 1 for L equal to k and equal to 0 for L not equal to k. So for L equal to k, this is minus lambda k, and since k is positive definite, this phi k transpose k phi k is always greater than 0. So this lambda k have to be negative. So this we have already seen during mode superposition. We are just revising it again because it will be required in the subsequent derivation. Now you assume that the phi n plus 1 here, the phi n plus 1 here can be written as this coefficient. This coefficient is time dependent. This coefficient is time dependent. So actually these are Cj's are Cj time n plus 1. So these Cj's are time dependent uh, into phi j. So this is some sort of we are assuming that this is the superposition of this each eigenvector is multiplied with a coefficient which is time dependent, and summation of that for all the eigenvectors is a value of phi at n plus 1. And these coefficient matrices, these coefficients, they actually change with time. Okay, sorry, here we made a mistake. So no. Yeah. So sorry, no, this is not a, this is a function of time, but here CJs, since CJs are function of time, actually we should write CJs are function of time. So from here, this is Cj at time tn plus 1. So this is Cj at time tn plus 1. And the solution phi n plus 1 depends on these coefficients into the corresponding eigenvector and the sum. So these Cj's are actually functions of time, but this is Cj at time n plus 1 into the eigenvector. So phi at n plus 1, phi at n plus 1 depends on Cj at n plus 1 into phi j is the eigenvector, and summation of that over all eigenvectors. Now if you assume the solution to be in this form, then you start with the homogeneous equation. That is, you make the right hand side 0. That you make the right hand side 0, and you start with the homogeneous equation. You start with the homogeneous equation and see if you start with the homogeneous equation, then whether the solution grows with time or not. You are starting with the homogeneous equation, whether it numerically grows. If it grows numerically, then your solution is unstable. So you start with not with this. Yeah, you start with actually you make the right hand side 0 and you start with this. You make the right hand side 0 and you start with this. That is the homogeneous equation. You start with the homogeneous equation, that is this part, and you assume that the right hand side, the forcing, not the right hand side actually, the forcing functions to be 0. So actually you start with this and you assume this solution and you substitute this solution for phi at n plus 1 and phi at n. So yes, this and this. Now you remove the summation sign for the sake of convenience and you assume that there is a summation over the repeated index. This k is the repeated index here. Now you pre-multiply it with phi L bar transpose, phi L bar transpose. Then only, so when you do this, phi L bar transpose k, phi k bar is minus lambda k. So you put for this minus theta lambda k, for this phi L bar transpose kt phi k bar equal to 1 for L equal to k. So this becomes 1 by delta t, and for L not equal to k it is 0. So here in the right hand side also this, and this divided by this is equal to this divided by this. So this is actually the ratio of coefficient at n plus 1 and at n. That means at tn plus 1 the value of ck, and at t equal to tn the value of ck, the ratio is this, and we want this ratio to be, we want the modulus of this ratio to be less than 1, so that this coefficient slowly decreases with time. And the decrease, if this rk is between 0 and less than 1, then it monotonically converges. But if it is between -1 and 0, that is RK is negative, between -1 and 0, there will be oscillatory convergence. That means this this is, say, suppose 0.9, then minus 0.8, then minus, then 0.7, then minus 0.6. So it converges in oscillations if RK is between -1 to 0. So this is Rk, and since lambda k is negative, we take one lambda k bar, which is minus of lambda k. So lambda k bar is positive. So we replace it here because it is convenient to think it in terms of a positive lambda k bar. And for numerical stability, your Rk has to be between -1 to +1, and if it is between -1 to 0, it is oscillatory stability, and if it is between 0 to 1, it is non-oscillatory stability. So this is same as saying that mod of Rk is less than 1. Now if Rk is less than 1, then your numerator has to be less than the denominator, and from that you get lambda k bar delta t is greater than 0, and this is always true because lambda k bar is always positive and delta t is the time step is also positive. So Rk less than 1 is always satisfied. Rk less than 1 is always satisfied. Then is Rk greater than 0? For that, this one has to be the numerator, this one has to be greater than this because the denominator is positive. So, and for that we get lambda k delta t is less than 1 minus 1 by 1 minus theta, and for Rk less than 0, then lambda k delta t has to be greater than 1 by 1 minus theta, and for Rk greater than -1, this has to be greater than -1, and if you do this manipulations, then you get lambda k is lambda k bar, sorry, so lambda k bar delta t should be less than 2 by 1 minus 2 theta. So -1 to less than -1 to 0, that is this between this is greater than 0 and less than this. So if you draw the graph, this is 1 by, this is lambda bar delta t equal to 1 by 1 minus theta. This is the graph, and if it is less than this and greater than this, that means lambda bar delta t is greater than 0 and less than 1 by 1 minus theta. That means greater than 0, that is this greater than 0 means it is actually Rk is less than 1 and Rk and lambda delta t is less than 1 by 1 minus theta means Rk greater than 0. So between these two, less than 1 minus 1 by 1 minus theta, less than 1 by 1 minus theta, and greater than this, that is means it is a stable system with no oscillations, a stable numerical scheme with no oscillation at all, and this is 2 by 1 minus 2 theta, and it is, and if you take the region greater than 1 by 1 minus theta and less than 2 by 1 minus 2 theta, it is stable, but it is stable with oscillations. And if it is greater than, if lambda k bar delta t greater than 2 by 1 minus 2 theta, it is unstable. So this portion is unstable, and here you can see. So as you keep on increasing theta, you cannot increase it beyond 1 because then it will become negative. So you can increase it up to 1. Then if it is 1, then it is infinite. So theta can go up to 1, and if you increase this theta, then this goes on and go, and it comes closer and closer to this line. And if it is 2 by 1 minus 2 theta, that is if you just increase theta, so maximum you can increase it up to half, and it goes towards this line. So below this line it is stable with oscillations, and between these two lines it is this between below this line it is stable with no oscillation. Between these two lines it is stable with oscillation, and above this line it is unstable. So